The universe feels ancient. 14 billion years is a number that already stretches the imagination. Civilizations rise and fall in the blink of geological time. Mountains erode, oceans shift, stars live and die. From our perspective, the cosmos has already been here forever. But in reality, it is still young. If the universe were compressed into a single human lifetime, we would be standing near the beginning, not the end. Most of its story has not yet unfolded. Most of its time has not yet passed. The future is longer than the past, far longer. When we look at the night sky, we see light that has traveled for millions or billions of years. It feels like we are witnessing something ancient and settled. But what we are actually seeing is an early chapter, a bright, energetic era filled with star formation, galactic motion, and constant activity. This era will not last. Stars are not eternal. Galaxies are not permanent. Even the structures that seem unimaginably stable today are temporary arrangements of matter and energy. And the clock is still ticking. In 1 trillion years, a span so large that human history becomes mathematically invisible, the universe will look nothing like it does now. The sky will not be filled with bright spiral galaxies. Star formation will not continue as it does today. Many of the processes we take for granted will have slowed, weakened, or ended entirely. But this transformation will not be dramatic. There will be no sudden collapse, no cosmic explosion signaling the end of an era. Instead, change will come quietly, gradually, almost imperceptibly at first. The universe does not end in noise. It fades. The most important thing to understand is this: the universe is not heading toward a violent finale. It is moving toward exhaustion, toward a state where energy differences flatten, motion slows, and structure becomes increasingly rare. Right now, we live in a time of abundance. Gas clouds collapse into stars. Stars forge heavier elements. Planets form. Black holes feed. Galaxies collide and reshape themselves. There is contrast, tension, imbalance, the ingredients that make complexity possible. But imbalance cannot last forever. Over immense timescales, the universe smooths itself out. Energy spreads, differences diminish. What was once bright becomes dim. What was once active becomes still. And 1 trillion years is only the beginning of that stillness. To truly understand what the universe will look like in that distant era, we must first accept something unsettling. We are living in the bright phase, a rare phase, a temporary phase. The night sky we see, full of light and structure, is not the default state of the cosmos. It is a fleeting configuration, a brief window when stars are still being born and galaxies are still alive with motion. In the far future, observers, if any exist, will not see what we see. They will inherit a darker sky, and that darkness will not come suddenly. It will arrive star by star, which means that to understand the universe in 1 trillion years, we must first understand what begins to disappear. Long before that, not galaxies, not black holes, but ordinary stars, the kind that quietly light up the present. Stars feel permanent. They rise every day. They anchor the sky. They seem as stable as gravity itself. For most of human history, stars were symbols of eternity, fixed lights that outlived everything below them. But stars are temporary engines. They shine because they are consuming themselves. At their cores, hydrogen atoms are forced together under immense pressure, fusing into helium and releasing energy in the process. That energy travels outward, balancing the inward pull of gravity. As long as fusion continues, the star lives in equilibrium. But equilibrium is not endless. A star like our sun has a limited supply of fuel. It burns steadily, calmly for billions of years. Compared to larger stars, it is patient. Compared to smaller stars, it is intense, and one day, it will change. Not violently at first. As hydrogen in the core becomes scarce, fusion shifts outward into surrounding layers. The star swells, its outer layers expand. It grows brighter and larger, entering what astronomers call the red giant phase. For nearby planets, this transformation is catastrophic. Mercury will be gone. Venus will not survive. Earth may be swallowed or scorched beyond recognition. But from a cosmic perspective, this is ordinary. Billions of stars like the sun are scattered throughout the universe. Each one is moving along a predictable timeline. Each one is slowly converting mass into energy. Each one will eventually exhaust its core fuel and evolve into something quieter. After the red giant phase, the outer layers drift away into space, forming glowing shells of gas. What remains is a white dwarf, a dense, hot remnant roughly the size of a planet, but containing much of the star's mass. It no longer shines from fusion. It glows from leftover heat. And then, slowly, it cools. In 1 trillion years, almost every star like the sun will have passed through this transformation. They will no longer dominate their systems with bright, steady light. Instead, they will linger as faint stellar corpses, slowly radiating away their remaining warmth. There will be no new sun-like stars forming to replace them, because star formation itself declines over time. Gas clouds, the raw material for new stars, are finite. With each generation of stars, more gas is locked away in remnants, planets, black holes, or dispersed too thinly to collapse again. The universe does not replenish its fuel, it consumes it. Right now, star formation continues in many galaxies, but it has already slowed compared to the early universe. The peak of stellar birth occurred billions of years ago. Since then, the rate has steadily declined. In 1 trillion years, it will be almost silent. No bright nurseries of newborn stars. No fresh clusters lighting up dark clouds. Only aging remnants and long-lived dim stars continuing their slow burn. And this is the first visible change in the distant future. Not an explosion, not a collapse, but the quiet disappearance of familiar lights. The sky of that era will not blaze with ordinary stars like ours. It will be populated by objects that are cooler, smaller, and far less luminous. The bright phase of the cosmos, the one we inhabit, will have faded into memory, if memory still exists. The end of sun-like stars is not dramatic. It is procedural, predictable, inevitable, a consequence of physics that cannot be reversed. And once these stars are gone, something deeper begins to change. Because when new stars stop forming, galaxies themselves begin to age. Not suddenly, but irreversibly. Right now, the universe is still creating. In distant clouds of gas, gravity continues its quiet work. Hydrogen drifts, gathers, compresses. Temperatures rise, pressure builds, and eventually a new star ignites, another point of light added to the cosmic tapestry. But this process is slowing. The universe is not an endless factory. It has a supply of raw material, cold hydrogen gas, and that supply is finite. Every new star consumes part of it. Every generation locks matter away in heavier elements, stellar remnants, black holes. Star formation peaked billions of years ago. What we see today is already the decline. Galaxies still shimmer with birth, but less than before. The brilliant blue glow of young stars is becoming rarer. Many galaxies have already exhausted their dense gas reservoirs. They are no longer nurseries. They are retirement homes. In 1 trillion years, this shift will be complete. No vast glowing clouds collapsing into brilliance. No clusters of newborn stars scattering radiation into space. No fresh ignition points breaking the darkness. The sky will stop replenishing itself. Imagine looking up and knowing that no new suns will ever rise again. Not tomorrow. Not in 1,000,000 years. Not ever. Light will only come from what already exists, and even those sources will be aging. Star formation is not just a visual phenomenon. It is the engine of chemical renewal. New stars forge heavier elements. Supernovae scatter them. Planets form from those enriched clouds. Complexity depends on cycles of creation and destruction. When creation slows, evolution slows. When evolution slows, structure stagnates. Galaxies in that distant era will look different. Spiral arms will fade. The contrast between bright clusters and dark voids will soften. What remains will be older stars, redder, dimmer, less energetic. The vibrant blues of youth will disappear first. Blue stars burn hot and fast. They live quickly and die violently. In 1 trillion years, none will remain. Even now, they are rare and short-lived. They are the fireworks of the cosmos, beautiful but brief. The future belongs to red dwarfs, small, cool stars that burn their fuel slowly, patiently, over enormous timescales. They do not shine brightly. They do not dominate the sky, but they endure for a time. In the era of 1 trillion years, the night sky will be darker, redder, and quieter. Light will still exist, but it will feel distant, muted. The energetic youth of the universe will be over. What remains will be longevity without renewal. And this is the first major transition of the deep future. Not destruction, not collapse, but depletion. The universe will not run out of light overnight. It will simply stop making new light. The old stars will continue shining one by one until their fuel is gone. And when the last large galaxies finish their star-forming cycles, the cosmos will enter a new age entirely. An age where what dominates is not creation, but endurance. And endurance eventually gives way to fading, because even the longest living stars are not eternal. And in the distant future, only the smallest ones will still be burning. Galaxies feel immortal. They stretch across hundreds of thousands of light years. They contain billions of stars. They collide, merge, reshape themselves over cosmic time. From our perspective, they are the largest stable structures in existence. But galaxies are not endless. They are reservoirs, and reservoirs can empty. Every galaxy begins with vast clouds of cold hydrogen gas, the raw ingredient for star formation. Gravity pulls that gas together. Stars ignite. Light spreads. Chemical complexity begins. But each generation consumes part of the supply. Gas is transformed into stars. Stars transform into remnants. Remnants lock matter away. Some material is recycled through supernova explosions, but never completely. With every cycle, usable gas becomes scarcer. What remains grows hotter, thinner, less capable of collapsing again. The universe does not refill these clouds, it expands. And expansion makes everything more distant. Over immense timescales, galaxies drift farther apart. Interactions become rarer. Fresh gas from intergalactic space becomes harder to capture. What a galaxy starts with is largely what it must survive on. In 1 trillion years, most galaxies will have used nearly all of their star-forming material. They will not explode. They will not vanish. They will simply stop creating. Spiral arms, those graceful structures lit by young blue stars, will fade. The glowing regions where new suns are born will darken. What remains will be older stellar populations, red dwarfs, white dwarfs, neutron stars, black holes. Galaxies will become quieter, not empty, but static. The vibrant swirling shapes we see today depend on constant renewal. Without new stars forming in their arms, spiral galaxies lose contrast. Over time, many will resemble elliptical systems, smooth, diffuse collections of aging stars with little internal activity. They will still orbit their centers. They will still contain immense gravitational power, but they will no longer evolve in the way we understand evolution now. The Milky Way itself will not escape this fate. Long before 1 trillion years pass, it will merge with the Andromeda Galaxy. The collision will reshape both into a single, larger system. For a while, star formation may briefly spike during the merger, but even that surge will consume what remains of the fuel. Afterward, the merged galaxy will slowly settle into silence. This is how galaxies die, not through violence, through exhaustion. They do not lose their stars immediately. Those stars continue shining for immense periods. But without fresh birth, a galaxy becomes a museum of old light rather than a factory of new brilliance. And in 1 trillion years, almost every galaxy will have entered this museum phase. The cosmos will still contain structure, but structure will no longer be dynamic. The age of galactic creativity will be over. What follows is not sudden darkness, but a gradual thinning of contrast. The brightest, most energetic stars will disappear first, then medium stars. Only the smallest, slowest burning ones will remain. And when even those begin to fade, the universe will move into an era that feels less like a continuation and more like a memory. Because what defines a galaxy today is not just its mass, it is its ability to create light. And when that ability ends, the universe shifts into something colder, quieter, and far more still. Not all stars die quickly. Massive blue stars burn fiercely and vanish in cosmic flashes. Sun-like stars live billions of years before fading into white dwarfs. But red dwarfs, the smallest true stars, follow a different path. They are patient. Red dwarfs burn their fuel with extreme efficiency. Their cores mix slowly, evenly. Nothing is wasted. Where larger stars blaze through their hydrogen in a few billion years, red dwarfs can shine for trillions. They are the quiet survivors of stellar evolution. In 1 trillion years, the universe will belong to them. By that time, every large star will be gone. Every sun-like star will have cooled into a white dwarf. Galaxies will no longer glow with young blue light. Only faint red points will remain scattered through the darkness. The sky will change color. Where once it shimmered with bright white starlight, it will now glow dimly with deep crimson hues. The cosmos will not be black yet, but it will feel subdued. The energetic youth of the universe will be long over. Red dwarfs are not dramatic. They do not swell into violent giants quickly. They do not explode as supernovae. They do not blaze brightly. They simply endure. For unimaginable stretches of time, These stars will continue converting hydrogen into helium at a steady, almost meditative pace. If any observers remain in that distant era, their skies will be ruled by these faint, long-lived suns. But even endurance has limits. Red dwarfs do not burn forever. Over trillions of years, even their fuel runs low. Slowly, imperceptibly at first, they will grow dimmer. Their output will decline. The balance between gravity and fusion will shift. Unlike larger stars, many red dwarfs will not become red giants. They lack the mass for dramatic transformations. Instead, they will quietly exhaust their hydrogen and contract into helium-rich remnants. They will become white dwarfs too, and eventually, they will cool. This marks a turning point, because red dwarfs represent the last generation of true, long-lived stellar engines. When they fade, the universe will lose its final sustainable light sources powered by fusion. After that, there will be no new stars igniting, no second chance. The age of stellar light will be over. The cosmos will still contain objects, remnants, black holes, drifting planets. But it will no longer generate fresh brilliance. Energy will only leak away, never renewed. And this transition will not be visible from one moment to the next. It will be gradual, star by star, red dwarf by red dwarf. Until one day, though no one will be there to mark it, the last active fusion reaction in the universe will cease. That moment will not shake space. It will not echo with sound. It will simply happen. And with it, the universe will step into a deeper, colder era. One defined not by burning stars, but by what remains after light is gone. White dwarfs, neutron stars, black holes, silent relics of a brighter time. After the last red dwarf fades, the universe will not go dark immediately. It will glow faintly, but the light will no longer come from fusion. It will come from leftovers. White dwarfs are not living stars. They are stellar cores exposed after their outer layers have drifted away. Roughly the size of a planet but containing the mass of a star. They are incredibly dense, matter compressed beyond ordinary intuition. They shine not because they create energy. They shine because they are still hot. A white dwarf is a cooling ember. In 1 trillion years, the universe will be filled with them. Every sun-like star will have become one. Every small red dwarf will have ended its life as one. Galaxies will no longer contain bright stellar nurseries, only scattered, fading remnants. The sky of that era will look unfamiliar. No bright blue giants, no warm yellow suns, no new constellations forming. Instead, dim white points, faint, cooling stars that once were luminous engines, will drift silently through space. White dwarfs cool extremely slowly. It takes trillions of years for them to radiate away their residual heat. During this time, they will gradually dim, shifting from brilliant white to dull red, then to infrared glow invisible to ordinary eyes. Eventually, they will become black dwarfs, theoretical objects that no longer emit visible light at all. But even before they fully cool, something important will change. White dwarfs do not sustain planetary systems the way main sequence stars do. Any planets that remain will orbit dead stars, receiving no fresh energy. Their surfaces will freeze, atmospheres will condense or escape, oceans will solidify into permanent ice. These worlds will not explode. They will simply fall silent. And across galaxies, this pattern will repeat. Billions upon billions of planetary systems orbiting faint stellar remnants, growing colder year after year, century after century, until time itself loses urgency. The universe will still contain mass. It will still contain structure. But activity, the kind we associate with life and transformation, will be almost gone. White dwarfs represent endurance without renewal. They are the final echoes of stars that once burned brightly. Their presence will stretch across immense spans of time, long after galaxies stop forming new light. Yet even this era is temporary, because white dwarfs cool, inevitably, relentlessly. They lose energy to the vast cold of space. Heat disperses, motion slows. The contrast between warm and cold flattens. And when enough time has passed, far beyond 1 trillion years, the universe will be populated not by glowing embers, but by dark, frozen, stellar corpses. This transition will mark the true end of the stellar era. No more burning, no more glowing, only remnants. And once the universe becomes dominated by remnants rather than stars, another force rises quietly to prominence: gravity. Because when light fades, mass still remains, and the most extreme forms of mass will begin to shape the next chapter. White dwarfs are not the final state of stars. They are a transition. For trillions upon trillions of years, these stellar remnants will continue cooling. They will radiate away their stored heat into an expanding universe that grows colder and emptier with time. No new energy will replace what is lost. Heat leaks, slowly, quietly, without reversal. A white dwarf begins intensely hot, hundreds of thousands of degrees at its surface. But it has no internal furnace, no fusion, no renewal. Its glow is borrowed from the past. Over immense spans of time, that glow weakens. White fades to red. Red fades to infrared. Infrared fades to darkness. Eventually, though the universe is not yet old enough for this to have happened, white dwarfs will become black dwarfs. A black dwarf is not explosive. It is not dramatic. It is simply cold. Cold matter compressed into extraordinary density, no longer emitting visible light. A silent sphere drifting through space, holding the memory of a star that once shone for billions of years. In 1 trillion years, most white dwarfs will still be glowing faintly, but the process toward darkness will be well underway. The cosmos will be entering what physicists sometimes call the degenerate era, a time dominated not by active stars, but by stellar remnants. Matter itself will feel different. Planets orbiting these remnants will have long since frozen. Oceans will have solidified into thick layers of ice. Atmospheres will have collapsed or escaped. Chemical processes will slow to near stillness. Without energy input, systems drift toward equilibrium. Temperature differences shrink. Chemical reactions slow. Movement becomes minimal. Galaxies will no longer look like swirling spirals. They will resemble diffuse clusters of cold objects, black dwarfs, neutron stars, wandering planets, and black holes. But something else will be happening beneath this quiet surface. Gravity does not sleep. Even in a dark, cold universe, gravitational interactions continue. Objects pass near each other. Orbits shift slowly over billions of years. Some planets will be ejected from their systems. Some remnants will collide. Some will spiral inward toward black holes. Time does not stop when light fades. It stretches. Over unimaginable durations, rare events become inevitable. White dwarfs may collide and briefly flare in renewed thermonuclear explosions. Neutron stars may merge in flashes of gravitational waves, but these events will be extraordinarily uncommon compared to the dynamic universe we know today. The dominant tone of this era is stillness, cold objects drifting in expanding space. And then comes an even deeper transformation, because black dwarfs are not perfectly stable forever. Given enough time, vastly longer than 1 trillion years, quantum processes and gravitational interactions can slowly alter even these dense remnants. Matter may tunnel, particles may decay, structures may reorganize in ways that are almost impossible to imagine on human timescales. The universe becomes patient. Events that seem impossible today become merely improbable over timescales measured in trillions and beyond. Frozen matter is not static in the absolute sense. It is simply moving at speeds and undergoing processes so slow that they blur into stillness. The sky of that era, if there were eyes to see it, would appear almost empty. Only faint infrared glows from cooling remnants, occasional flashes from rare collisions, vast distances between points of light. Darkness becomes the default. Light becomes the exception. And yet, even this frozen universe is not the final stage. Because among the cold remnants, one class of object grows increasingly dominant, not in number, but in gravitational influence. Black holes. While stars faded and white dwarfs cooled, black holes continued to gather mass. They do not rely on fusion. They do not cool in the same way. They endure differently. In a universe of frozen matter, gravity becomes the primary architect, and the deepest wells of gravity will define the next era. An era where black holes are no longer rare extremes, but the central players in a darkening cosmos. When the last red dwarfs fade and white dwarfs cool into near darkness, the universe will not be empty. It will still contain worlds. Planets will still orbit the remnants of stars that no longer shine, but these worlds will no longer belong to illuminated systems. They will exist in perpetual night. Right now, planets are defined by their stars. Their climates, atmospheres, and chemical cycles depend entirely on a steady flow of energy from fusion. Remove that light, and the character of a planet changes fundamentally. Oceans freeze from the surface downward. Atmospheric gases condense and fall as frost. Winds stop. Weather disappears. The sky loses color. In 1 trillion years, most planets will orbit faint stellar corpses. Their suns will no longer burn. Instead, a dim white dwarf or a completely dark remnant will sit at the center of a frozen system. Any warmth that once defined those worlds will have dissipated into space long ago. Surfaces will become rigid. Ice will accumulate in layers kilometers thick. Atmospheres, if they survive at all, will thin and settle into stillness. Some planets will not orbit anything at all. Over immense spans of time, gravitational interactions destabilize systems. Stars pass near one another. Orbits shift slowly. Some planets will be ejected from their systems entirely, cast into interstellar space. These rogue worlds will drift alone through a dark universe with no primary star, no sunrise, no seasonal cycle. They will not explode or collapse. They will simply exist. Without external energy, internal heat becomes the only remaining source of activity. For a while, radioactive decay and residual formation heat may keep cores warm. Subsurface oceans might persist beneath thick shells of ice, but even this energy declines. Heat radiates outward and disappears into expanding space. Over time, every planetary process slows. Tectonics freeze, magnetic fields fade, chemical cycles stall. The distinction between surface and interior becomes less meaningful as everything approaches uniform temperature. A planet becomes a monument of matter rather than a dynamic system. And yet gravity continues to bind these objects together in loose systems around dark remnants. In the absence of bright stars, the architecture of former solar systems will still exist, though altered and simplified. Massive planets may remain in stable orbits around white dwarfs. Smaller bodies may collide occasionally in rare gravitational encounters, but the scale of activity will be almost incomprehensible compared to the present era. Imagine standing on such a world, if standing were possible. The sky would not be black in the way our night sky is black. It would be deeper than that, absent of distant galaxies, because expansion will have carried most beyond visibility. Only the nearest gravitationally bound remnants would remain. The cosmos would appear small and dim, not vast and radiant. Planets without suns redefine the meaning of environment. They are not hostile in a violent sense. They are silent. They are thermally exhausted. They are stable in a way that removes all possibility of change. This is the difference between destruction and depletion. Destruction is energetic and visible. Depletion is quiet and final. As these worlds drift through the degenerate era, they will represent the memory of a brighter universe. Their rocks contain elements forged in long-dead stars. Their structures reflect past gravitational dances, but nothing new will emerge from them. The age of planetary weather, oceans, biospheres, and climates will be over. And yet, even in this deep freeze, something continues. Because above these dark worlds and at the centers of former galaxies, black holes remain. They do not cool in the same way. They do not depend on fusion. They gather mass slowly. They merge. They dominate gravitational landscapes. In a universe filled with frozen planets and cooling stellar corpses, black holes will become the most powerful remaining engines of change. Not engines of light, but engines of gravity. And as the cosmos grows colder and dimmer, these objects will begin to shape what little structure remains. As stars fade and planets freeze, gravity does not weaken. It becomes more obvious. In a universe no longer illuminated by constant stellar birth, the deepest gravitational wells begin to dominate the structure that remains. Black holes, once rare and exotic objects in active galaxies, slowly become the central pillars of the dark era. Today, most large galaxies contain supermassive black holes at their centers. These objects weigh millions or even billions of times more than the Sun. In the present universe, they are often hidden behind bright accretion disks and energetic jets, feeding on gas and dust pulled inward by gravity. But as star formation declines and gas supplies are exhausted, their behavior changes. They do not stop existing. They simply wait. Over immense timescales, galaxies merge. Their central black holes spiral toward each other, orbiting slowly as gravitational waves carry energy away. Eventually, they collide, forming even larger black holes. This process repeats across cosmic history. With each merger, the number of black holes decreases, but their masses grow. In 1 trillion years, most surviving galaxies will have already combined into larger gravitationally bound systems. Star formation will be over. White dwarfs, neutron stars, and frozen planets will drift in wide, slow orbits. And at the center of each massive structure, a black hole will remain, heavier than ever. These objects will not shine brightly anymore. Without abundant gas to feed on, their accretion disks will thin and fade. Jets will weaken. To a distant observer, they will appear almost invisible. But invisibility does not mean insignificance. Black holes exert control without light. Their gravity governs the motion of surrounding remnants. Over time, close encounters between stellar corpses and black holes become more likely. A white dwarf may wander too close and be torn apart. A neutron star may spiral inward after millions of slow gravitational interactions. Each rare event produces a brief flash of radiation, one of the last bright signals in an aging universe. But such events become increasingly uncommon as distances grow and structures thin out. The expansion of the universe plays a critical role here. As space itself stretches, galaxies not gravitationally bound drift beyond visibility. In the far future, observers within a galaxy will see only their own cluster of remnants. Everything else will have receded beyond the cosmic horizon, unreachable and unseen. The universe will feel smaller, not physically smaller, but observationally limited. Within each gravitational island, black holes will represent the largest reservoirs of mass and the deepest wells of potential energy. They are the last objects capable of dramatically altering their surroundings, even in a darkened cosmos. And yet, they too are not eternal. This is the quiet irony of the deep future. The most stable and dominant objects in the universe will also be temporary. Black holes seem indestructible. Nothing escapes them once it crosses the event horizon. They appear as final endpoints of gravitational collapse. But quantum mechanics introduces a subtle correction. According to theoretical predictions, black holes emit an extremely faint form of radiation, now known as Hawking radiation. It is not visible in any practical sense today because it is vastly weaker than any other energy source nearby. But in a universe where everything else has faded, this faint emission becomes significant. Black holes lose mass, not quickly, not dramatically, but inevitably. In 1 trillion years, this process will have barely begun for supermassive black holes. Their lifetimes are staggeringly long, far longer than the current age of the universe. But once the stellar era has ended and frozen remnants dominate space, black holes will slowly begin to evaporate. They will shrink imperceptibly at first. Over spans of time so vast that 1 trillion years becomes a short chapter, these giants will radiate away their mass particle by particle. The larger the black hole, the longer it survives. The smaller ones will vanish first, releasing faint bursts of radiation in their final moments. In that distant epoch, black holes will be both the rulers and the ticking clocks of the cosmos. They will define the structure of what remains. They will gather the last drifting remnants. They will merge and grow. And then, over unimaginable durations, they too will dissolve. The universe will pass from a bright age of stars to a dim age of remnants, to an era where black holes are the final architects of change. And when even they begin to disappear, the cosmos will enter something stranger still, an era not dominated by objects, but by the gradual thinning of existence itself. Because when black holes fade, the universe loses its last concentrated sources of gravity. What remains after that is not darkness in the ordinary sense. It is diffusion, and that diffusion will define the true deep future. Even before the last stars fade, something else has already begun reshaping the future. The universe is expanding. Not like an explosion into empty space, but like space itself, stretching between objects. Every second, distant galaxies move farther away. The farther they are, the faster they recede. This expansion is not slowing. In fact, it is accelerating. Right now, this expansion is subtle. Galaxies are still visible in vast numbers. Telescopes capture clusters and filaments stretching across unimaginable distances. But this view is temporary. As trillions of years pass, expansion isolates. Galaxies that are not gravitationally bound to one another will drift beyond each other's cosmic horizons. Light emitted from them will never arrive. Signals sent across that growing distance will never be received. They will not explode or vanish. They will simply disappear from view. In the distant future, observers within a galaxy will see only their own gravitationally bound system. Everything else will have receded beyond detection, carried away by the stretching fabric of space. The universe will appear empty, not because it lacks matter, but because that matter has become unreachable. Today, the observable universe spans billions of light years. In a trillion years, the observable region for any given observer will shrink dramatically. Not physically, but practically. The accelerating expansion ensures that distant galaxies cross a boundary beyond which information cannot travel back. The sky will grow darker, not because stars have all died yet, but because neighboring galaxies will fade into invisibility. Imagine looking up and seeing only the remnants of your own merged galaxy. Perhaps the Milky Way and Andromeda combined into one massive elliptical structure, surrounded by vast blackness. No faint smudges of distant galaxies, no cosmic web, no evidence of large-scale structure beyond your local cluster. The universe will feel finite, self-contained, solitary. And this isolation is permanent. Expansion driven by dark energy does not reverse under current understanding. It continues indefinitely. Structures that are not gravitationally bound today will never become bound in the future. Distance increases faster than gravity can compensate. This means that the universe will fragment into cosmic islands. Each island will contain whatever matter remains gravitationally connected. Stellar remnants, black holes, frozen planets, dark matter halos. Beyond that island, nothing observable will remain. This is one of the quietest but most profound transformations of the far future. It is not the death of stars. It is not the evaporation of black holes. It is the loss of connection. Communication between galaxies becomes impossible. Travel beyond a local cluster becomes physically unattainable. Even light cannot bridge the growing gap. The cosmos transitions from a connected network to isolated pockets, drifting in a vast expanding void. And within each pocket, time continues. Black holes merge, white dwarfs cool, frozen planets wander, rare gravitational encounters occur. But these processes unfold in solitude, cut off from the wider universe that once existed. The night sky of that era would not reveal cosmic history. There would be no visible evidence of the Big Bang, no redshifted galaxies receding at the edges of vision. The expansion itself would be undetectable without ancient records. Observers born in that distant time might conclude that their isolated island is the entire universe. They would see no proof otherwise. This is how expansion reshapes reality, not through violence, but through separation. And as isolation deepens, the internal processes within each cosmic island continue toward their own conclusions. Black holes grow, matter thins, energy disperses. Eventually, even within those islands, structure becomes unstable, because gravity, though powerful, cannot prevent entropy, and entropy is patient. In a universe of isolated galaxies and fading remnants, the next transformation will not come from motion, but from thermodynamics itself, from the slow, inevitable leveling of energy differences across all remaining space. When that leveling completes, the universe will enter its coldest phase yet. Not a dramatic ending, but a final equilibrium. After the stars have burned out, after galaxies have stopped forming new light, after expansion has isolated every gravitational island from the rest of the cosmos, the universe will enter a phase dominated not by radiance, but by gravity. This will be the era of black holes. In earlier epochs, black holes were dramatic phenomena. They consumed gas, powered quasars, shaped galactic centers with violent jets of radiation. They were luminous in indirect ways, surrounded by bright accretion disks that revealed their presence. In the far future, they will no longer shine that way. There will be little gas left to consume. Few stars will wander close enough to be torn apart. Accretion will slow to near stillness. Black holes will remain, massive and silent, anchoring what little structure is left. Yet silence does not mean inactivity. Over trillions of years, gravitational interactions will continue within each isolated galaxy. White dwarfs, neutron stars, and frozen planets will occasionally pass near one another. Some will be ejected into interstellar darkness. Others will spiral inward, slowly losing orbital energy. Eventually, many will fall toward the central black hole. Not dramatically, not in bright flares, but gradually, through rare, slow interactions that accumulate over unimaginable time. Black holes will grow. Smaller black holes formed from individual stars will merge with one another. These mergers will release gravitational waves that ripple outward through space, though there will be few observers to measure them. With each collision, the number of black holes decreases, but their mass increases. Over vast spans of time, galaxies will simplify. What once contained billions of luminous stars will become dominated by a handful of ultramassive black holes and scattered stellar remnants orbiting at extreme distances. Structure compresses, complexity declines. The era of black holes is not energetic in the way the stellar era was energetic. It is gravitationally intense but thermally quiet. There is less radiation, less contrast, less visible change. Black holes will represent the final concentration of matter. They will be the last objects capable of meaningfully altering their surroundings. Their gravitational pull will slowly reorganize what remains of galaxies. Over quadrillions of years, even stable orbits will degrade. Stellar remnants will be flung outward or consumed. Eventually, many galaxies may reduce to a dominant central black hole surrounded by a sparse halo of drifting objects. And then, something subtle begins. While black holes seem permanent, quantum mechanics predicts otherwise. They are not completely black. At the edges of their event horizons, quantum effects allow tiny amounts of energy to escape. This process is unimaginably slow for large black holes, but it never stops. They radiate, Not light in the conventional sense, but particles, a faint emission now called Hawking radiation. In the present universe, this radiation is negligible compared to all other energy sources. But in the deep future, when stars are gone and matter is frozen, it becomes significant. Black holes will begin to lose mass. At first, the change is imperceptible. A supermassive black hole may take far longer than 1 trillion years to noticeably shrink. But the clock has started. As the era of black holes unfolds, evaporation becomes the central process shaping the cosmos. The largest black holes will survive the longest. Smaller ones will vanish first, ending in brief bursts of energy when they reach critical mass. These final flashes will be among the last bright events in the universe. After that, only the largest gravitational giants will remain, slowly dissolving. The era of black holes will last far longer than the era of stars. It will stretch across timescales that dwarf everything before it. But even this era is finite. Gravity gathered matter. Gravity concentrated structure. But even gravity cannot resist entropy forever. When the final black holes begin to evaporate completely, the universe will cross another threshold. There will be no more dominant objects, no more engines of structure, no more concentrated mass shaping space around it. What remains will be thin, diffuse, and almost uniform. The universe will no longer be defined by objects. It will be defined by emptiness. And in that emptiness, only one process will continue: the quiet leveling of energy toward absolute equilibrium. Black holes seem like final answers. They swallow matter. They trap light. They compress stars into singularities hidden behind event horizons. For a long time, it was believed that once something fell into a black hole, it was gone forever. But physics is rarely that simple. In the 20th century, a subtle insight changed the story. Quantum mechanics, the theory governing the smallest scales of reality, does not allow perfect stillness. Even in empty space, particles flicker in and out of existence. The vacuum is not silent, it is restless. Near the edge of a black hole, this restlessness matters. At the boundary called the event horizon, pairs of particles can briefly appear due to quantum fluctuations. Normally, such pairs annihilate each other almost instantly. But at the horizon, one particle may fall inward while the other escapes. To an outside observer, it looks as though the black hole is emitting radiation. This emission is unimaginably faint for large black holes. A supermassive black hole emits less energy than the cosmic background radiation that surrounds it today. In our current era, Hawking radiation is practically undetectable. But in the deep future, when stars are gone and the universe is cold, it becomes the dominant process. Black holes lose mass, very slowly at first. The larger the black hole, the slower the evaporation. A stellar mass black hole would take far longer than the current age of the universe to noticeably shrink. A supermassive black hole would take vastly longer still. Timescales so enormous that trillions of years become minor intervals. But the process is relentless. Evaporation accelerates as the black hole shrinks. Smaller black holes radiate more intensely. When they approach their final stages, they release bursts of energy before disappearing entirely. In that distant epoch, these bursts will be among the rarest and brightest events left in the cosmos. Imagine a universe already dark. No stars, no glowing galaxies, only frozen remnants and vast expanses of near-empty space. And then, occasionally, a final flash, the death of a black hole that has endured since the early universe. After that flash, nothing remains at that location. No singularity, no event horizon, just radiation dispersing into space. As time stretches beyond comprehension, even the largest black holes will succumb. One by one, they will evaporate. The gravitational anchors of galaxies will dissolve into diffuse energy. The era of black holes will end not with collapse, but with fading. And when the last one disappears, something extraordinary happens. The universe loses its final concentrated reservoirs of mass. There are no more objects capable of reshaping structure on large scales, no more deep gravitational wells, no more engines of dramatic transformation. What remains is sparse, particles drifting, photons traveling through expanding space, occasional electrons and positrons encountering one another in rare interactions. Structure gives way to distribution, energy differences flatten, temperatures approach uniformity. The cosmos becomes simpler, not because it was destroyed, but because it was diluted. Hawking radiation represents the ultimate undoing of gravity's work. Where gravity once gathered matter into stars and black holes, quantum mechanics slowly disperses it again. Concentration becomes diffusion. Form becomes uniformity. And with that, the universe approaches its quietest state yet. Not a violent end, not a sudden void, but a gradual thinning into something almost featureless. And beyond that thinning lies the question that has haunted cosmology from the beginning. What does a universe look like when there is almost nothing left to happen? That answer waits in the next stage, not defined by objects but by entropy itself. After the last black hole evaporates, the universe will not explode into nothingness. It will not collapse inward. It will not reverse direction. It will simply continue expanding, now largely empty of structure. But even then, something may still remain. Matter, atoms drifting through space, protons and neutrons locked inside what was once stellar debris, electrons orbiting in quiet simplicity. Even in an exhausted universe, particles may persist, unless they do not. One of the deepest unanswered questions in physics concerns the stability of protons. In the standard model of particle physics, protons are treated as effectively stable. No experiment has yet observed one decaying. But many grand unified theories predict that protons are not eternal. They simply decay extremely slowly, not over billions of years, not over trillions, but over timescales so vast that they dwarf the age of black holes. If protons are unstable, then matter itself has an expiration date. In that case, even after the stellar era, even after the era of black holes, the universe will continue to simplify. Atoms will not remain forever. Over unimaginable durations, protons may spontaneously transform into lighter particles, perhaps positrons, neutrinos, and photons. Solid matter will dissolve, not in explosions, not in heat, but in isolation. A lone proton drifting in space may simply change, its identity rewritten by quantum processes. A white dwarf that survived until the era of black holes would, over extreme timescales, gradually disassemble from within. Matter will not shatter. It will fade. If proton decay is real, then the universe's future becomes even quieter than previously imagined. No long-lived atoms, no permanent remnants. No enduring rocks or stellar corpses, just a thin gas of elementary particles moving through expanding space. and the expansion never stops. As space stretches, the density of particles decreases. Collisions become rarer. Interactions become almost non-existent. Energy spreads thinner and thinner, approaching uniformity. Temperature approaches absolute zero. Not exactly zero, but closer and closer, asymptotically. Entropy reaches near maximum. This stage is sometimes called the heat death of the universe. It is not death in a biological sense. It is thermodynamic exhaustion, a state where no free energy gradients remain to power processes. No imbalance remains to drive change. In such a universe, nothing dramatic happens. That is the point. There are no new stars, no new black holes, no new structures forming. Only particles drifting, occasionally interacting, slowly redshifting as expansion stretches the wavelengths of radiation further and further. If proton decay does not occur, matter may remain locked in degenerate remnants forever. But even then, gravitational interactions over extreme timescales could destabilize them. Given enough time, almost anything possible becomes inevitable. The difference between permanence and patience becomes meaningless at these scales. The universe moves toward simplicity, from plasma to stars, from stars to remnants, from remnants to black holes, from black holes to radiation, from radiation to near uniform thinness. Each stage is quieter than the last, and yet, even in this near-empty future, physics does not disappear. Quantum fluctuations still occur, space still expands, particles still obey their laws. The cosmos does not cease, it stabilizes into monotony. The grand structures that once inspired awe will be gone. What remains will be sparse and nearly featureless, a faint bath of low-energy radiation and occasional particles separated by distances so vast that interaction becomes almost impossible. This is not annihilation, it is dilution, and once dilution completes, the universe enters its final recognizable phase, a state where nothing significant happens not because it cannot, but because there is no longer any imbalance to make it matter. The story does not end with silence, it ends with stillness. And in that stillness, meaning changes. Because meaning, like structure, depends on contrast, and contrast will be almost entirely gone. After stars, after black holes, after matter itself dissolves. What remains is not dramatic emptiness. It is something thinner. The universe does not become nothing. It becomes almost uniform. A vast, expanding field of extremely low energy radiation and isolated particles drifting in distances so large that interaction becomes extraordinarily rare. Space continues to stretch. Wavelengths of photons grow longer and longer. Radiation cools. What was once bright starlight becomes microwave glow, then radio whisper, then something even weaker, stretched beyond any meaningful temperature scale. Energy does not disappear, it spreads. Entropy approaches its maximum not through violence, but through evenness. Temperature differences fade, density differences fade, structure dissolves into distribution. Imagine an ocean, but not of water. An ocean of near-empty space containing scattered particles separated by distances that make galaxies seem crowded by comparison. In this thin sea, a single particle might travel for unimaginable spans without encountering another. Interaction becomes the exception, uniformity becomes the rule. If proton decay has occurred, then atoms are gone. If it has not, remnants may still drift, but gravitational encounters will be so rare that they effectively cease to matter. Everything that once defined cosmic architecture, Stars, galaxies, clusters, black holes will have reduced to faint imprints in an ever-expanding background. Time continues, but nothing significant happens. And this is the crucial shift. Earlier eras of the universe were defined by transformation. Gas collapsed into stars, stars forged elements, galaxies collided, black holes merged. Even their evaporation marked events. Now, there are no events, only drift. Even quantum fluctuations, those tiny, restless movements of vacuum energy, become the most dynamic processes left. On extremely small scales, particles may still appear and disappear, but these flickers do not build anything lasting. The universe becomes thermodynamically flat, and flatness has a strange character. It is not hostile, it is not chaotic, it is simply neutral. Without gradients, without hot and cold, dense and sparse, no work can be extracted, no structure can arise, no new complexity can form. The cosmos approaches equilibrium, not perfectly perhaps, because perfect equilibrium may never be reached in a finite time, but close enough that change loses meaning. This is the state physicists call heat death. It is not a dramatic extinction, it is the absence of possibility. In such a universe, if consciousness somehow existed, it would witness no stars, no galaxies, no motion beyond slow drift. The sky would not even be black in the way we understand blackness. There would be no contrast against which darkness could be defined, only uniform dimness. And yet, even here, expansion continues. Space grows larger, distances increase, radiation redshifts further. The thin sea becomes thinner still. The universe does not stop. It empties. And in this emptiness, the most profound realization emerges. The bright, structured cosmos we inhabit is not the default state of reality. It is a temporary imbalance, a brief flare of complexity between two vast stretches of simplicity. The hot, dense early universe and the cold, diffuse far future. We live in the middle of that flare, and when it fades completely, the universe will not end with noise or collapse. It will end with dilution so complete that nothing remains to mark the passage of time except the expansion of space itself. Which brings us to the final question. If this is the direction of everything, if stillness is the ultimate horizon, what does that say about the meaning of motion, life, and structure in the brief era where they exist? That is where the story closes. Not in physics, but in perspective. If we follow the timeline far enough, beyond stars, beyond galaxies, beyond black holes, beyond even stable matter, the universe does not explode. It does not collapse inward. It does not tear itself apart. It fades into equilibrium. This is the most unsettling part of the future. Not because it is violent, but because it is calm. The universe does not rage against its ending. It simply exhausts the differences that once made change possible. Energy spreads evenly. Temperature flattens. Density approaches uniformity. Without gradients, nothing can happen. No engines run, no stars ignite, no structures grow. Time continues, but time loses character. In earlier eras, time was measured by transformation, the birth of stars, the collision of galaxies, the cooling of planets. In the final state, nothing marks its passage. Without change, time becomes abstract. The universe does not end with a final event. It ends with the absence of events. This is sometimes called heat death, but the term can be misleading. It suggests something abrupt, something catastrophic. In reality, it is a gradual smoothing of everything into sameness. The bright universe we know, filled with light, motion, tension, is not the natural resting state of reality. It is a temporary deviation, a rare configuration where imbalance allowed complexity to bloom. We live in that deviation. Between a hot beginning and a cold dilution, there exists a narrow window where stars burn, planets form, chemistry evolves, and consciousness arises. That window is small compared to the total lifespan of the cosmos, and yet it is everything we know. In 1 trillion years, much of that brightness will already be gone. In timescales far beyond that, even the memory of structure will dissolve. If observers exist then, they will inhabit a universe radically different from ours, darker, quieter, smaller in appearance. Or perhaps there will be no observers at all. That possibility is not tragic. It is thermodynamic. The universe does not guarantee persistence. It does not promise renewal. It allows processes to unfold according to laws that neither favor nor oppose complexity. Structure emerges. Structure dissolves. And between those two states, for a brief moment measured in cosmic terms, something looks up and asks what comes next. The deep future tells us something subtle. Not that the universe is meaningless and not that it is doomed. It tells us that contrast is rare, that imbalance is precious, that the bright era, the era of stars and galaxies, is not permanent. We are living during the luminous phase of reality. That alone is extraordinary. Because when the cosmos finally reaches its thin, uniform state, when energy differences are gone and motion no longer matters, there will be no record of the long journey that led there. Only quiet space, expanding indefinitely. And in that stillness, the universe will not be broken. It will simply be complete.